Welcome to the MOOCs course Transport Phenomena of Non-Newtonian Fluids. The title of this lecture is Continuum Hypothesis and Transport Mechanisms. Till now in last 3 weeks what we have seen? We have seen different aspects of non-Newtonian fluids, their classifications, their examples, and then mathematical models for non-Newtonian fluids. Then how to measure the rheology of an unknown fluid. If the fluid is non-Newtonian and then viscoelastic, how to measure the normal stress, and then in addition to the normal stress, conventional shear stress versus shear rate information, how to measure by different types of rheology, and all that. Those things we have seen with the appropriate example problems wherever required, right. So, because till now what we have seen, we have seen the basics required knowledge of non-Newtonian fluids, because this course is on transport phenomena of non-Newtonian fluids. We have seen adequate information about non-Newtonian fluids, which would be more than sufficient with respect to this contents of this course, right. Now, before going into the details of applying the transport phenomena concept for this non-Newtonian fluids, then what we will have now, we will be having a kind of a recapitulation of a few basics of transport phenomena, like transport phenomena, continuum hypothesis, transport mechanisms, equations of change for isothermal system, equations of change for non-isothermal systems, etc. The derivation of those equations of change, all those things we are going to see in this particular week. So, now we have a kind of basics of transport phenomena in this particular week, starting with the concepts of continuum hypothesis and then transport mechanisms. Why do we need to study the transport phenomena? Basically, if you see, because if you have the knowledge of transport phenomena, then designing or controlling the operating of any of the unit operations or unit processes or the entire plant could become very convenient to the engineers. That is the reason transport phenomena knowledge is very much essential for chemical engineering grads. So, because of that reason we are having a UG level core transport phenomena course. If the same transport phenomena course is advanced level, like advanced transport phenomena or like transport phenomena of non-Newtonian fluids, that is again a kind of a core course for the PG level chemical engineering students, right. So, how it is essential? Why that much essential having the knowledge of transport phenomena for chemical engineering grads? That we see with a few basic examples. Let us say you have a flow through pipes. In the pipe a fluid is flowing. So, for a required flow rate, how much pressure drop should you maintain? If you wanted to calculate, you need to have a knowledge of transport phenomena. If you have several pipes connecting different types of unit operations and unit processes, then what is the friction factor or what are the frictional losses because of these connections, etc. Those things if you wanted to understand, you need to have a knowledge of a transport phenomena. Then let us say you have a vertical column and then that column is packed with some kind of material, like beads, glass beads or crushed glasses or sand, etc. Such kind of material is used for that packing of a column, and then a fluid is flowing through that column because of some requirement of either reactions or heat transfer purpose or whatever it may be. So, there also you need to have a kind of knowledge what is the frictional pressure drop, or in order to maintain a certain flow rate, how much pressure drop you have to maintain, what is the friction factor, all those things if you have the knowledge, so then you can comfortably design the packed columns, or you comfortably make modifications to the operating conditions if at all required. So, not only for the design, but also controlling the operational of any of the unit operations, unit processes or the entire plant, the chemical engineering grads need the knowledge of transport phenomena. Okay. So, let us say if the flow through pipes or packed column, if you also have a kind of temperature gradient, so then how the temperature gradient is going to affect this pressure drop versus volumetric flow rate or friction factor, etc., how that is going to be affected because of the variations in the temperature from one location to other location, then again you need to have a knowledge of transport phenomena. Okay. So, likewise if you take some other examples like flow of a fluid along spherical particles along or a cylindrical particle, and then associate heat transfer is also very common phenomenon in majority of chemical engineering plants. So, then there also you need to have the knowledge of transport phenomena, so that you can properly operate it or tune the operating conditions, or you can even design them if required. Then diffusion of species from falling film, another example. In polymeric industries, usually it is often required to have a polymeric films of very small thickness, 1 mm or even less. So, then usually these dilute polymer solutions are allowed to flow along the inclined or vertical surface, and then while they are flowing along these inclined surfaces, etc., they are also dried, so that we can have a kind of thin film kind of things are very common examples. So, at what rate this polymeric solution should be allowed to flow, so that to required thickness film should form. That if you wanted to know, then you should know the evaporation rate, diffusion rates, etc. All those things are required. So, if you wanted to understand those concepts, then again you are required to have the knowledge of transport phenomena. Similarly, like evaporation of column of liquid, then boundary layer flows past flat plates and associate heat and mass transfer to surrounding fluids, wherever you need to have the rate of heat transfer, rate of mass transfer, etc., those kind of calculations. So, then this transport phenomena knowledge is going to be very essential. So, like that if you keep on listing, you can have a n number of applications in chemical industries, or almost all chemical industries you will find the requirement or knowledge of transport phenomena almost like ubiquitous for any part of a plant you consider. Okay. So, that means a priori information on performance of industrially important settings can be achieved if you have a adequate knowledge of transport phenomena. Okay. These transport phenomena include three closely related topics. The first one is transport of momentum related to the fluid mechanics part, transport of energy related to the heat transfer part, and transport of chemical species related to the mass transfer part. Okay. So, these are the processes like transport of momentum, transport of energy, transport of chemical species are essential. So, if you see only fluid mechanics point or heat transfer point or mass transfer point, all these courses we have already done before doing the transport phenomena courses in general any university UG curriculum. So, then why are we doing this transport phenomena course again as a core course? That also because they occur simultaneously, or rather having only one transport process or transport of only one momentum or only transport of energy or only transport of chemical species is a kind of exception rather than a rule. But in this fluid mechanics, heat transfer or mass transfer, wherever you take individually, like fluid mechanics, you take only macroscopic transport phenomena, that also without considering the effect of concentration variations, temperature variations, how it is going to change the flow phenomena, etc. Those kind of things we in general do not take into the picture. Similarly, when it comes to the heat transfer, only heat transfer part only we have studied in the heat transfer course in general. So, that is indirectly the variations in the velocity distribution, how it is going to affect the overall heat transfer phenomena or local heat transfer phenomena, that those things we have not studied. So, that means the heat transfer combined with the momentum transfer is not studied in heat transfer course in general. Even if it is studied may be a small bit, not in detail. So, similarly the same is true for the mass transfer part also. We see specific to the transport of chemical species without having the knowledge of how the momentum transfer is going to affect the transfer of this chemical species from one location to the other locations. But in reality, in majority of industrial settings, these transport phenomena problems they occur simultaneously rather than individually. Then governing equations are also very closely related. Right. So, if you write the transport of equations of change for momentum, for energy, for concentration of a species A, then you can compare. So, these equations are closely related, very much closely related. We are going to derive those equations in the next class anyways. So, there we can realize. In fact, if you remember from your UG level course, so then what we have, momentum transfer equations, let us say U component, we have so, let us say x component of momentum equation, and then in the x direction velocity component, if you designate with u, then x component of momentum equation in Cartesian coordinates, if you write, this is what you have. So, u is in the x direction, v is in the y direction, w is in the z direction. The velocity components in 3 different directions are u, v, w. Then this is what you have. Let us say you have the heat transfer part equation, if you see. So, then rho Cp for simplicity, I write these equations like this by taking this u outside, and then here by taking this v outside, and then here by taking this w outside of this differentiation. So, now if you see these equations here, so all these equations, they are quite similar. So, the temporal variations and then space variations in these properties, whether it is temperature or momentum, they are very same, except this pressure term is additional term here in the momentum equation. But without that, if you compare the momentum equation and energy equation, they are very similar to each other, very close to, in the form wise they are very similar. They are very similar, and then if you write the species concentration equation, then that will be even much more similar. The energy equation and species concentration equation would be very much similar to each other. So, that is the reason the governing equations, these are the equations, generalized equation where the transport is there because of the convection, and then molecular transport, etc., all those things are there. So, then these equations are closely related to each other and they are similar to each other. Okay. Since they are closely related and similar to each other, their solution approach would also be similar, it is quite possible. Then molecular mechanisms are also very closely related. So, whether the heat transfer or momentum transfer, these terms, whatever these 3 terms are there, they indicate the transport because of the convection. Alright. So, similarly here these 3 terms, they indicate transport of the energy because of the convection. Okay. Whereas these right hand side, these 3 terms, they indicate the transport of momentum because of the molecular mechanism, right. Whereas here again these 3 terms in the energy equations, they indicate transport of the energy because of the molecular mechanism, that is by conduction. Okay. So, the mechanisms which are leading for the transport of whether it is momentum, transport of whether it is energy, transport of whether it is concentration, the molecular mechanisms are also quite similar. Only thing that in the molecular part, the material property is also coming into the picture, but convective part, the nature of the material is not coming into the picture at all. Only thing that the bulk motion, what is the velocity? What is the velocity in x direction, what is the velocity in y direction, what is the velocity component in the z direction, that is only coming into the picture if you take the convection part only. I assume that all these equations are already known to you in your UG level course, so then I have directly written, but we are going to derive these equations again, we are going to discuss them in detail wherever we required. So, this is what we see. So, now what we understand from these equations are similar, they are occurring simultaneously, equations are similar. So, then solution approaches are also similar, and then also molecular mechanism which are leading the transport of these properties are also similar, right. Because of this reason, so we need to study transport phenomena as a separate course, despite we have studied the fluid mechanics, heat transfer and then mass transfer individually. So, transport phenomena at different levels, what does it mean? So, from this slide we will also realize that transport phenomena is how it is different from the fluid mechanics, heat transfer or mass transfer part that we have studied previously. So, for that purpose what we do, we take a continuous stirring reactor we take here. So, in which we are already having a B component at concentration Cb0. So, to this reactor Ca0 the component A is added at a concentration Ca0. The temperature of that component feed material coming in is Ti, then material is coming at Fi flow rate. Okay. So, then when it comes and joins the B component in the reactor, so then A plus B giving rise to C reaction is taking place, and then product is being collected out because C is product now here. So, then that product is collected out at Tf temperature and then at flow rate Ff. So, whatever the unreacted A and B are there, so those things again we are separating and then putting them back into the reactor as a recycle. So, this is the process here. So, this transport phenomena is possible at three different level: macroscopic level, microscopic level and then molecular level. In the macroscopic level, what we worried about or we consider only the quantities that are entering and then that are leaving, at what rate, at what they are entering to the system, at what rate they are leaving, or we are worried about these properties, whichever property may be. Properties when I call, when it can be temperature, pressure, velocity, density, concentration, stress, etc., anything it may be. It may be any quantity, any property that you wanted to measure. So, the property, how much it is entering, how much it is leaving, that much only we are concerned in the case of macroscopic level, and then the difference whatever is there, that we relate to the accumulation, if at all any accumulation. Right. So, we do not worry what is happening inside the reactor, whether the concentration is uniform, changing, how it is changing in one location to other location, that we do not at all worried about those kind of thing in macroscopic level. Right. And then scale is in general some centimeters to meters in the case of macroscopic level. But what we understand, whether it is temperature, whether it is concentration, whether it is velocity, whether it is density, whatever you take, any property you take, it is not going to be uniform at each and every location. At each and every location it is not going to uniform, that we know, actually, right. So, we realize that is the reason sometimes you may get the different values of different when you repeat the experiments, right. But what happens, the properties, they are not uniform, in the entire reactor, they are changing from one location to the other location. So, if you wanted to consider those changes, then what you do, you subdivide the system into the small control volumes like this, right. and then see that properties, whatever the property is there, that you assume that that's uniform within the small control value, because that is the reason the variations are there, but variations are varying from one location to the other location. So, now you take a region of a certain location that we call a small control value. So, within each control volume these properties may be same, but the property may change when we move to the neighboring control value, right. So, the properties may be changing, it may be increasing, decreasing depending on the system, and the change may be large, change may be small, we cannot say, but there may be change. So, that change you consider by writing the equations for this microscopic level, right. So, that is what we say. In the microscopic level, what we do, we subdivide the system into the small control volumes, and then within each control volume we say that the properties are uniform, but when we move from one control volume to the other control volume, properties may change, and then that change may be small or large depending on the gradients, right. Such a way that we write the constitutive equations and solve them to get the interior details what is happening. Okay, all those things we see, and then this is very much essential, because in sometimes many a times at corners the mixing may not be proper. At the corners mixing would be inefficient. So, at these locations primarily the already whatever the B present, that is only there, the C and A may be very less at these corners. So, those kind of inequalities would be there. So, if you wanted to understand those kind of things, then you have to do this microscopic level transport phenomena, where the length scale is few microns to centimeters, right. So, that is the microscopic level transport phenomena, but within the each control volume we have the large number of molecules, huge number of molecules would be there, and then so all those large number of molecules are interacting amongst themselves. So, when they are interacting, there may be change, there may be transport of property from one molecule to the other molecule, maybe because of the vibration, because of the rotation, because of the interaction, or oscillation, whatever the nature of molecule, whatever the thing that is happening between the molecules, whether interaction because of the vibration, because of the rotation, because of oscillations, because of just translation, there may be interaction, and then because of that interaction transport or change of properties may be taking place, right. So, if you are considering those level changes in the properties, then we call that transport phenomena at molecular level, where the scale usually few nanometers or microns. So, in the macroscopic level transport phenomena, we develop equations called macroscopic level balances, where we are concerned with quantities or properties at entry and exit points of system for a change occurred in the system, and then does not consider details of what is happening inside the system. Length scale is in general order of centimeter or meter. Then in the microscopic level, we consider interior details of system, where we try to find out what is happening to the mixture in the small region within the system. Then we develop equations of change for mass, momentum and energy within the small region, and then that we integrate to the overall system, right, if required. So, that is what we do. So, primarily the course that we are going to study is handling developing of these equations, and then using these equations to solve engineering transport phenomena problems. So, here the length scale is usually order of micron to centimeters. In the molecular level, what we have fundamental understanding in terms of molecular structure and interaction forces, and then these details are usually important from the theoretical physicist or physical chemist point of view. But however, such details are also essential in processes where engineering grads are involved. So, some examples like if we have a complex molecules, extreme ranges of temperature or pressures or chemically reacting systems, etc., then we also need to have the knowledge of this molecular level, and then length scale usually up to 1000 nanometers. So, whether it is macroscopic level or microscopic level or molecular level, the conservation laws play a key role at all levels of transport phenomena. So, the maintaining of conservation of momentum or energy or species whatever is there, that is very essential at all levels of transport phenomena. So, that means transport phenomena at microscopic level is considered here in where we are considering the continuum hypothesis is valid without any restrictions. Okay. So, that part only we are considering in this course. So, obviously, a recapitulation of few basic concepts of transport phenomena such as continuum hypothesis, transport mechanisms, and hence constitutive equations of transport by molecular mechanisms are essential. So, that is what we are going to see now. So, what is continuum hypothesis? Continuum hypothesis, it says that physical properties are assumed to be distributed throughout the space. Physical properties means what? What kind of properties? It may be velocity, it may be temperature, it may be pressure, it may be density, stress, electric field strength, etc. It may be any property that is associated with the system whichever we are considering. Okay. And then we are assuming as per the continuum hypothesis, these properties are assumed to be distributed throughout the space without any without any locations where these properties are being infinite or not being defined. So, the continuum hypothesis does not allow it. Okay. They have to be distributed throughout the space, and then every point in space should have finite values for such properties whichever we are considering. And from one point to the next point, the properties may change, the property may change, the velocity may change from one point to the other point within the system, the temperature may change from one point to the other point within the system. There may also be discontinuity of the properties, whether temperature, pressure or velocity, stress, density, whichever it may be, there may be discontinuities may also be possible, alright, or discontinuities because of the jump. What does it mean by how the jump of the fluid will take place? Let us say you have a spherical particle, right, and then there is a fluid flowing around it, right. So, the density of the particle rho p is usually very large, compared to the density of fluid any fluid that you take. So, right at the surface the density is jumping from very high density rho p to some moderately low some other density low density rho. So, the jump is is very high. So, such kind of discontinuities may be there, but we cannot have the case where the property is becoming infinite or to be undefined at any single stage. So, that is not allowed. This is what about basic requirements of continuum hypothesis, right. We assume the physical properties are distributed throughout the space, and then every point the property has the finite values, and then from one point to the other point when you move, the property may change and there may even be discontinuous jump as defined here, but we cannot afford to have any location the property being infinite or not being defined. Okay. So, precisely in simpler language, if you wanted to explain this continuum hypothesis, let us say the same reactor that we are taking here. Okay. So, this is the system, only this part where the fluids are being interacting or the reaction is taking place, let us say. So, this space we are subdividing into very small control volumes like this. So, the entire space whatever is there, that we have subdivided into the small infinitesimally small spaces. So, that the property here, let us say at this property, so that at this level property may be something, right. At this level it may be something, at this level it may be something, at this level may be something and different values it may be there compared to the property at this level. Okay. But within the control volume, within each control volume, the property is going to be uniform, What does it mean by, let us say this completely shaded control volume, completely filled control volume here, whether you take at the center of the control volume, either at the corner of the control volume, at the wall of the control volume, any location within the control volume, the property, whichever the property you are taking, the temperature or density, velocity, anything, stress, anything that you are trying to measure, they are going to be uniform. right. But the very next control volume, if you consider, then the property may be different, T1, rho 1, for example V1 I am saying, it is not a different fluid, same fluid. The property from this control volume to this control volume has changed. There is a possibility that change may be small or large, that depends on the gradient, but that is changing. But any control volume you take, within the control volume the property is going to be uniform, the property is going to uniform, that is one thing. So, that is how you have to divide the system into the small. That means you cannot have a very bigger control volume. If you take very bigger control volume, obviously from one corner to the other corner of control volume the properties may change, you may not have the uniformity, right. So, but again you cannot take very small control volume, that within the control volume you may be able to accumulate only 5 or 10 molecules, like that only. Why we cannot have such small control volumes? Because if you wanted to have the uniform properties within the control volume, the molecules should go infinite number of interactions amongst themselves, so that local thermodynamic equilibrium should be maintained. That local thermodynamic equilibrium, when it is maintained, then only the properties are going to be uniform within the control volume. So, that is the important thing. You have to have a control volume very small size, but it cannot be very small that you cannot have a sufficient large number of molecules. Again you cannot have the control volume very big size, that the property is changing from one location to the other location within the same control volume. From one control volume to the other control volume it will anyway change. Okay. So, those are the important thing about this continuum hypothesis, that is precisely the reason in which physical properties to be described are subdivided into a set of infinitesimal volume elements, each of which simultaneously following that each volume element should be small enough so that properties are uniform. That is, any spatial variations in properties inside the control volume or volume element are negligible. That is, within each control volume or volume element the properties are going to be uniform. Spatial variations are not allowed within the control volume. From one control volume or from one volume element to the other volume element it is possible. That is how we are doing. Then each volume element should be large enough to contain statistically large number of molecules. Why we need large number of molecules? Because the local thermodynamic equilibrium should be maintained. So, what is the connection between local thermodynamic equilibrium and large number of molecules? Because when you have the large number of molecules, infinite number of collisions amongst those molecules possible, which will establish the local thermodynamics, right. So, such way you divide the system and then for each control volume you write the balance equations, then you develop the differential equations. Those equations are nothing but the so called momentum equations, equations of change for momentum, energy and then species concentration that we are going to discuss in transport phenomena course in general. Okay. So, continuum hypothesis holds well provided all dimensions of system are large compared to the molecular size. Okay. That is how the control volumes are being made small sizes, right. But its violation is possible. Let us say if you have a diffusion of a gas in a porous media in a pore. So, the size of the pore is very small and then the molecule sizes size of the molecules are anyway small. So, then under such conditions the dimensions of the system and then molecular size of these components are of the same size, comparable to each other, right. So, but under such conditions we cannot have the local thermodynamics maintained. Indeed, local non-thermodynamic equilibrium would be there. So, because of that one, under such small systems we cannot impose the continuum hypothesis, that is flow of gases in small pores where Knudsen diffusion is occurring. That is one of the example where we cannot say the continuum hypothesis holds well. Then basic problem in continuum mechanics is to describe the response of material to stress. A qualitative statement of that response is known as the constitutive equation. Okay. So, when a material is applied certain kind of force, so then or how to a applied stress, how the material is responding. right. So, that is what we try to understand. We try to understand in continuum mechanics the response of material to applied stress. So, that response, if you write as a qualitative statement, we call them as a constitutive equation, that is a model which describes how a material will respond to stress. Okay. So, now we see the transport mechanisms. So, whether temperature or chemical concentration of the material, if you are perturbating it so that they become non-uniform, then what happens, whatever the gradient developed because of the perturbation, that will tend to disappear over time. Okay. Then the same is true for velocity variations within the fluid. In terms of temperature concentration, it is very easy to realize. So, then same is true for the momentum as well within a fluid, right. And then spontaneous dissipation of such gradients is a fundamental and far reaching observation. Okay. So, that is the energy, concentration of material and then movement of fluid. What is happening according to these statements, when there is a perturbation has been given, then there is a non-uniformity. The non-uniformity whatever is there, that causing the gradients, and those gradients are tending to disappear over time. So, those gradients are going to disappear over time from which region to which region, from high intensity region to the low intensity region they are going to transport, that is they move from regions of higher to lower intensity levels. The transport of those properties, whether it is energy, concentration or momentum, how it is going to occur, right, how it is going to move from one region to the other region. So, that depends on the transport mechanism. So, there are the two contributions are there. So, convective transport which accompanies any bulk motion, and then molecular or diffusive transport which originates from intermolecular forces and relative motion of the molecules, right. So, the momentum equation and then energy equation I have written a few slides back. So, there we can see the convective transport, it has taken considered the bulk motion, that is velocity components only, because of the velocity how the property is changing, how the temperature is changing, that part is only included in the energy equation, convective part. Okay. So, whereas the molecular or diffusive transport which originates from intermolecular forces and relative motion of the molecules, that is there in the right hand side of these equations, that we see anyway. So, convection part can be described in a general manner. So, if you get back those equations, momentum equation and energy equation and then species concentration equation that we have written a few slides back, whatever the convection part, they are very similar, right. Rho Cp, rho V, those kind of terms were there in the left hand side, okay, and then their spatial variations were there, right. So, that is only velocity, spatial variations in the velocity, the spatial variations in the temperature because of the bulk motion velocity, those things are only there. So, that means convection part can be described in a general manner. So, what does mean by general manner, whether the fluid is benzene or water or cyclohexane or toluene, that part is not coming into the picture in the left hand side of those equations, momentum equations or energy equations, whichever you take, right, that part is not coming into the picture. So, only part is coming into the picture at what velocity is it moving, given fluid is moving, that part is only coming into the picture. That is the reason convection part can be described in a very general manner. However, molecular part of transport processes are specific to given material or class of materials, like in the right hand side, whatever the viscosity mu is there. So, it depends on the material, what fluid it is, Newton, whether it is water, benzene, cyclohexane. So, accordingly its viscosity is coming into the picture. Similarly, energy equation, the thermal conductivity, that K is coming into the picture. So, it is going to be dependent on the material, from one material to the other material, like that. Okay. So, whatever the right hand side part those equations are there. So, that is because of the molecular part, those are dependent on the nature of the material or a group of the materials. Okay. So, these equations, the molecular fluxes are related to the material properties, whatever the transport because of the molecular mechanism is occurring. So, that molecular flux is related to the material properties and gradients of temperature, concentration and velocity if at all they are involved. So, molecular fluxes are related to the material properties and gradients of temperature, concentration and velocity, all three, if all three transport phenomena are occurring. Okay. So, now that is the reason we are going to see now some of the equations, molecular mechanism, by molecular mechanism how the change in the transport of energy is taking place, because of the molecular mechanism how the diffusion or the mass transfer is taking place, because of the molecular mechanism how the momentum transfer is taking place, that is what we are going to see now. Constitutive equations of transport by molecular mechanisms. Heat conduction, Fourier's law, if you remember, it is heat flux, that is energy per unit cross section area, vector, it is a vector, is proportional to temperature gradient as Q is equals to minus K del T. Del T is the temperature gradient, K is the thermal conductivity, Q is the heat flux, it is vector, and then temperature gradient, that is also a vector. That is also a vector. Individual temperature is not vector, but gradient of it is a vector. Okay. So, both of them are having in the moving in the same direction, Q and del T both will be having the same direction. Okay. So, in a moving fluid, heat flux vector represents energy transport relative to the mass average velocity. Otherwise, if you have a kind of definition of this heat flux related to the fixed coordinates, then convective contribution will also come into the part. So, if you wanted to write equation only for transport because of the molecular mechanism, then the flux has to be represented related to the mass average velocity only. If you take the fixed coordinate related to the fixed coordinates, then convective contribution will also come into the picture. In this equation, K has no preferred direction, whereas the flux has the same direction as that of temperature gradient. So, such kind of materials are known as the isotropic materials, which include most of the solids and almost all fluids, and materials that are anisotropic have an internal structure that makes thermal conductivity depend on the direction also. So, that in this equation wherever this K is there, that K is scalar K is replaced by the tensor K. So, dot product between tensor and then vector, because this del T is nothing but a vector, T is a scalar but del T is a vector. So, dot product between tensor and then a vector will give you vector. So, then that is the reason Q is still having the direction this one. So, in this case the Q and del T may not be having the same direction, they may be differing from each other. Okay. So, such kind of equation is true for anisotropic material. Similarly, species diffusion, Fick's law if you write, mass flux of species relative to its mass average velocity again. Why mass average velocity? Because you are writing the equation only for the molecular transport mechanism only. If you take fixed coordinate related to the fixed coordinate, then contribution because of the convection will also come into the picture. That is the reason mass flux of species A relative to its mass average velocity is proportional to its concentration gradient, and then that is written here. J is the mass flux of A, rho is the density of the mixture, it is not density of individual A or B, but it is a mixture density. DAB is nothing but diffusivity of A and B, and then WA is nothing but the mass fraction of this component. The same equation, if you take the rho WA, then that can be written as a CA, that is nothing but concentration of that component A. Okay. So, DAB is the diffusivity of A into B, rho is density of binary mixture, WA is the mass fraction of A in the binary mixture, CA is the concentration of species A. So, that is about the molecular transport of energy and then species concentration by molecular mechanism. Now, what about the molecular mechanism or transport of momentum by molecular mechanism? That is what we are going to see. So, stress and then momentum flux. local rates of momentum transfer in a fluid are determined by the stresses in general. So, consider a point within a fluid through which an imaginary surface having an orientation is described by a unit normal n. Stress at that point with respect to the orientation of test surface is given by stress vector S n. So, let us say this is the surface you are taking, and this surface you are representing by some normal vector, that normal vector is n. So, at this point on this surface, if you take at this point whatever the stress vector is there, so that is nothing but S. Okay. So, this stress is defined as the force per unit area on the test surface exerted by the fluid toward which n points. Okay. So, it has two components, normal component and then tangential component. There is only one single normal component, but there are two tangential component. So, pictorially if you see the same surface whatever we have taken in the previous slide, which is described by this normal vector n. So, then in the normal direction whatever the stress is there, that we call Sn, that is normal stress, and then two tangential stresses whatever are there. So, in this direction S2 and then in this direction S1, right. So, Sn is nothing but normal stress, S1, S2 are nothing but tangential stresses. Okay. So, normal component represent a normal stress or pressure on the surface, whereas the tangential components are nothing but the shear stresses. Okay. This stress vector is related to stress tensor sigma by this equation. Sn is equals to n dot sigma, dot product between a normal vector and then stress tensor. So, that will be giving a vector, stress vector S. Okay. So, this sigma in Cartesian coordinate if you write, you have these 9 components: sigma xx, sigma xy, sigma xz, sigma yx, sigma yy, sigma yz, sigma zx, sigma zy, sigma zz, like this. So, these have two components, one is the isotropic pressure component, another one is the viscous component. So, the same thing we can write minus p plus tau xx in place of sigma xx, and then in place of sigma xy simply we can write tau xy, and then in place of sigma xz we can write simply tau xz. Likewise, tau yx minus p plus tau yy, tau yz, tau zx, tau zy minus p plus tau zz. That is, this is we can represent sigma, we can represent as sigma, the components whatever the 9 components are there, general way we can represent as sigma ij is equals to minus p Kronecker delta ij plus tau ij. And then if I is equals to j, then del I and the Kronecker delta ij would be equals to 1. That means when x is equals when I is equals to x and then j is also equals to x, then we have the sigma xx is equals to minus p plus tau xx as we have written here. Let us say if I is equals to x and then j is equals to y, then Kronecker delta ij is equals to 0, then sigma xy is nothing but tau xy as we have written here. That is a generalized representation of each component sigma ij. Right. For example, sigma xy is the force per unit area on a plane perpendicular to y axis acting in x direction and exerted by fluid at greater y. That means, it has 3 parts: j specify a reference plane, and then I specify the direction in which it is acting, and there would be a sign convention whether it positive or negative. Positive or negative, that is depends direction, moving backward or forward, that way we have these directions. Further, this ij, different way people represent. Some books, they are written, they are used in a different way. Maybe I specifying a reference plane and j specifying the direction in which the stress is acting. Okay. So, stress may be interpreted as momentum flux in the case of fluids. Parts of stress caused solely by fluid motion is termed as viscous stress, and this viscous stress contribution to stress tensor is denoted by tau, and for Newtonian fluid with constant viscosity Newtonian fluid with constant density and then viscosity, this viscous stress is related to the local velocity gradient by this equation. Tau is equals to minus mu del V plus del V transpose, where mu is the viscosity of the fluid, del V is the velocity gradient, del V transpose is the del Vt is nothing but transpose of the velocity gradient. And then if you take a unidirectional flow where only one component of velocity Vx is existing and then it is function of y, then we will be having only one stress component tau yx is equals to minus mu dvx by dy. This is what in general we write for a definition of Newtonian fluid basically, but complete definition is this one. So, now we see analogy of these molecular transport mechanisms for the case of momentum transfer, for the case of energy transfer, for the case of species concentration change. Okay. So, let us say heat transfer, we have this equation, that same thing we are writing minus alpha d by dy of rho Cp T, okay, where alpha is nothing but k by rho Cp. Then mass transfer, we have this equation, this we can write it as minus dAb dCa by dy, and tau yx we are writing minus nu d by dy of rho Vx, where nu is nothing but mu by rho. Now, in these three equations what we have, the gradients d by dy is there, okay, all three cases, and then in the case of heat transfer we have the property, change in property or gradient of rho Cpt, and then in the case of mass transfer, the gradient or change in concentration with respect to variations in y direction, that is what we have. Here in the momentum flux rho Vx we are having. So, they are very similar, right, d by dy of whatever the property is changing in the energy in the mass transfer and in momentum transfer, right. So, this whatever this alpha, this dAb and then this nu we are having, they are similar, they are dependent on the material property, because alpha is k by rho Cp, rho k are depending on the material to material. Diffusivity of A may not be same diffusivity of A in B is not going to be same for the case of diffusivity of A in C. So, that depends on material to material. Same is here, viscosity and then density of a fluid are changing from one fluid to the other fluid. So, then this is going to be different. However, all of them are having same units of meters per second. So, that is the analogy, that thermal diffusivity alpha, binary molecular diffusivity dAb and then kinematic viscosity nu, all of them are having units of meter square per second. Okay. So, what is the importance of writing this analogy? Now, we understand, right. So, that is, their ratios will provide a comparison of intrinsic rates of different transport processes if more than one transport is occurring simultaneously. At the beginning of the lecture, we said that transport phenomena, more than one transport process may be occurring simultaneously. That is the reason, if you wanted to solve the problem, which transport do you need to prioritize, which you do not, you cannot, you do not need to worry about, or you really worried about all the transport processes to be occurring simultaneously, really worthy to consider simultaneously. All those analysis, if you wanted to understand, you can have the ratios of this thermal diffusivity, molecular diffusivity and then kinematic viscosity, etc. So, then you will have a kind of a rational which is important, which is more, which is less, like that, which type of transport or transport of which property is more essential to be considered, those kind of thing you can realize. Let us say ratio of viscous momentum transfer related to the heat conduction is Prandtl number, where nu by alpha is nothing but Prandtl number, that you can write mu Cp by k. Let us say in a process the momentum transfer is taking place and then heat transfer is also taking place. So, in the process, whether to consider the interaction between these two processes important or not, that you can realize from this number. If it is very large, then then you can say that momentum transport is going to be leading the process. If it is very small, then you can say the conduction heat transfer due to conduction is going to leading the process. That kind of understanding you can have. Similarly, rate of viscous momentum transfer relative to species diffusion is Schmidt number. So, where nu by dAB is nothing but Schmidt number, that we can write mu by rho dAB. How much important is the role of viscosity and density compared to the role of diffusivity in a given transport process, that you can realize or you understand from this Schmidt number. Okay? Or should you worry strongly about the diffusion part in the momentum transfer part or not, should you worry about the role of diffusion, mass diffusion or molecular diffusion in a process where both momentum and then mass transfer are occurring, that you can consider by taking this mu by rho dAB number. Okay. If it is very large, then you can say the role of diffusivity is very small, and then you can consider the transport phenomena or momentum transfer without worrying the effect of diffusion in the transport of momentum. Like that you can analyze. Similarly, ratio of diffusivities that arises in the analysis of simultaneous heat and mass transfer is Lewis number, that is alpha by dAB. Okay. So, that is the reason that we have written the analogy of transport of momentum, energy and then species concentration by molecular mechanism. So, that we can have a kind of rational understanding which transport process is going to lead and then how much essential given a transport process if more than one transport phenomena is occurring simultaneously. In the next class, we are going to discuss the derivation of equations of change for isothermal systems. The references for this lecture, this one, primarily the entire lecture is prepared from this reference book, Analysis of Transport Phenomena by Dean, but however, other books would also be equally useful, especially this Panton and then Bird, Stewart, Lightfoot. These books will also provide adequate knowledge about whatever the things basics that we have discussed in this particular lecture. Thank you.